Good evening. Today we have Dr. Frank Ascoli again for another fantastic lecture. We're going to be talking about morning QA with image-guided radiotherapy and table shifts this afternoon, this evening. And so I'm going to hand it over to Frank, and hopefully you guys will really enjoy this lecture. Yeah, take it away, Frank.
Thank you so much, Tia. I hope everyone can hear me okay. Tia, can you nod your head if you're hearing me okay? Very good. Thank you. Okay. And welcome to all the participants worldwide. Again, I feel it's such an honor to be asked by RCC to give these lectures to our colleagues throughout the world. It's a very nice thing we do, especially in these COVID times when we can't meet in person at these meetings anymore. So thank you very much for joining in this lecture. This lecture is Morning Quality Assurance with image-guided radiotherapy and very, very important table shifts. As many of you know, the American Association of Physicists in Medicine, the AAPM, the group that I belong to and many of you belong to also, has published extensively on daily, monthly, and annual QA. The importance of QA, quality assurance, cannot be overstated. I like to tell my therapists when they arrive in the morning, it's really you who are doing the very important tests to make sure that today, when you're going to be turning on the machine and giving these large doses of radiation, that your machine is working correctly and that the dosages to the patients can be delivered safely and accurately. The therapists are the first line in the morning. Usually, at least in my experience, physicists get in a little later because we tend to work a lot later. And we let the therapists run very important daily quality assurance tests, which of course physicists have set up the testing procedures and have established the tolerance levels. The question, of course, is what happens if a machine fails any of the important morning tests? And the answer that I give is do not hesitate to call me, even if it means waking me up out of a sound sleep, because I've been working well into the morning hours. If a machine is not operating correctly, I want to know, and I want to be able to advise the therapists on what to do, whether they should treat the patients or wait for me to get in or call service. So the morning QA is very important. It combines elements of machine quality assurance with state and federal regulations. In the US, most of the linear accelerators, all of the linear accelerators, were licensed with the various state radiation control agencies, and the state agencies, issue regulations that the therapist must follow every morning to make sure that the machine is safe to use on their patients. We're going to go over much of this testing today with some slides that show you how we do it in my clinic. The AAPM task group number 142 came out with a report which supplements the very important task group 40 report, which was really a major report addressing all aspects of quality assurance. TG40 came out before the age of IMRT, stereotactic radiosurgery, stereotactic body radiotherapy. So TG40 had to be supplemented with TG142 testing that recognized the complexity of modern machines, especially having to do with imaging and image guidance. So here is a table that shows some of the daily testing required by the Task Group 142 report. Dosimetry, which we'll cover later on, has to do with X-ray output constancy. Now, the key word is constancy, not calibration. The therapists are not testing the calibration of the machine. The therapists are making sure that the output is within a range that the physicist has set. So that range is kept to 3% of a value that the physicist determines. And if the output falls within 3%, then the machine, at least from a constancy point, is okay to use. The radiation output falls within a range that's been established by the medical physicist. That has to do with both X-ray and electrons. So if the machine is being used for electron treatment, then the electron output must also be measured. Mechanical tests are important, and as you can see, that the mechanical tolerances vary depending upon what the machine is used for. There's laser localization, the distance indicator, the ODI, optical distance indicator, and also the collimator field size indicator. And notice how for machines which are used for stereotactic radiosurgery or stereotactic body radiotherapy, that the tolerances become tighter as the precision of the machine becomes more crucial with delivering these very, very high single doses or several doses of high dose radiation. And that was a big change with TG142. It established much tighter mechanical tolerances for machines that are used for stereotactic radiosurgery or SBRT. Safety is very important, and in the US, if any of these do not work, you cannot treat the patient. So say, for example, that my therapists come in and they find that the door interlock is not working, that the beam does not shut off if the door is open. Well, in the United States, most states have said that if the door interlock doesn't work, you cannot treat the patient that day. Even though you can see the patient, even though you may have someone posted by the door to make sure nobody accidentally enters the room, many of the states, at least the states that I work in, say that you cannot treat the patient that day. The door interlock must be working in order for the machine to be safe to use. Audio visual, very important. You have to be able to see and hear the patient. Now, some of the other tests, which we're going to go into, are the imaging tests that TG142 made specific guidelines on. Planar KV and MV imaging, which is portal imaging, has certain requirements for testing. Of course, there's collision interlocks. Make sure that the collision interlocks are working. If anything touches these imaging panels, then the machine must stop moving because there is a danger of harming the patient if the interlock is not working. Sometimes the patient is very close to these devices and they may contact the patient, and there's a danger of hurting the patient if the interlock is not working. Very important is positioning and repositioning. And that means that are the image guidance systems that you're using, either planar KV-KV or cone beam CT or even MV imaging on certain machines. Does the positioning guidance software accurately bring you to within 1 millimeter of where you're supposed to be treating if you're using stereotactic radiosurgery? Many places use cone beam CT with their onboard imager. I know at my center, we use cone beam CT on every head and neck patient, on every lung patient that we're treating with IMRT. We use cone beam CT with every prostate patient that we're treating with IMRT. We do that on a daily basis because we feel it's so accurate to be able to target and treat the areas that need to be treated. And because the radiation is delivered with such precision, you want to be sure that what you are targeting is actually being treated within a millimeter accuracy. And we'll go over some of those tests later on in this talk. Here's an example of two very common machines, the Varian machine on the left and the Electa machine on the right. And both machines have the ability to take portal imaging with the megavoltage beam here and here, or using a X-ray tube KV imaging at 90 degrees to the MV imaging. Here's the X-ray tube on the Electa machine. There's the imaging panel. These panels use a amorphous silicon detector. It's electronic imaging, no need to develop films. The images appear very quickly on a monitor, and the therapist can evaluate those images with software provided by the vendor. We'll talk more about that too. But the first test that I had mentioned was audiovisual monitoring. Very important. You have to be able to see the patient and hear the patient. Most centers like to use two cameras. Not only do you see the patient from a different angle, but if one camera breaks, doesn't work, you always have the backup camera, the second camera working, so you do not have to cancel treatments that day if a camera is malfunctioning. As I mentioned, the door interlock must be tested daily and has to work. In the United States, there is a requirement, even for linear accelerators, that there has to be a radiation room monitor. It must flash red when the beam is on. It seems a little silly, I know. It's an electronic machine. It's not cobalt. The source isn't going to get stuck in the on position, but many states require still a radiation monitor to show when the beam is on. Audiovisual monitoring, laser checks, and distance indicators, all part of daily QA performed by the radiation therapist before the first patient is treated. Sometimes it's hard to schedule these QA procedures, especially in a super busy department where you just about have enough time to treat hundreds of patients that you may be treating. And yet it's so important to have time set aside in the morning to start the machine and run these tests. Very important to make the time early in the morning to run these tests before you treat your first patient. There are different devices that will let you project the radiation to light field on it, and you can check the SSD, you can check the lasers to see that the lasers are at the right SSD. I'll show you some of those devices in the next couple of slides. Here's one such device. These cubes are very important, and there are several vendors that make these cubes. These cubes have the ability to test a number of different things. So for example, you see here a 10 by 10 field, and there are marks that show you it's a 10 by 10 field, so you can quickly check field size. You can quickly check laser centering here, and here's the sagittal laser. You can check by rotating the gantry that the light field also agrees with the laser. I am getting a little feedback, so I think somebody has to mute them. Somebody has to mute their microphone because I'm getting feedback. I'm sorry. A very important thing that these cubes have is a device, a phantom, a object that's embedded away from the central axis. And that is going to allow you to run your image guided testing. So very important with these phantoms. Not only do they check geometric accuracy, but they also give you the ability to target something that's off axis, shift the table using the software, and be sure that you're in the right place. I'll show you more about that. Here's another common device called PentaGuide. This PentaGuide has isocentric markings. It has an object that is off center to the isocenter. So if you were to set your crosshairs here and here, you would be on a device that is off axis, and you could shift to that to see if the shift software is working correctly. The guide also has some other low contrast objects embedded in it, and that is useful for image quality testing. So daily geometric testing with one of these guides, you place it on the table, you level it, and you set your isocenter at the crosshair, and you can check a field size on the top of it. We use a spirit level on the gantry to check gantry angles. And then as we rotate the machine around to a lateral position, does the crosshair agree with the laser? And we like to see that within 1 millimeter. Here is a homemade device that does the same thing, a cube with graph paper on it, and a leveling platform and a spirit level. If you're doing MV imaging and you want to check the quality of the image, objects are visible inside using MV to see if you can detect the low density object and at least have some sense that the portal imager is working correctly. Here is another device. It's an aluminum plate with many, many holes drilled into it. The holes go from very deep to very shallow, and the holes vary in diameter. So you can test to see the limits of your portal imager. When I run this test, I use it on the portal imager and I put some coins along each side. So I can also check the light field, radiation field edge at the same time using coins, and I can check the quality of the portal imager. Table shifts, as I mentioned, are extremely important in radiation therapy. Image guidance really is based upon accurate targeting of the tumor and then shifting the table to that point. Now, on this object, you have the isocenter here, but you also have an object here. So what you can do is take an image of the object, KV image, anterior and lateral, target the image, target that object that's off center, use the software to shift the table to that position, and then re-image it. Very, very important test to make sure that your table shifts are going in the right direction and that your targeting system is working correctly. So here's the first image here, uses a reference image. You can see how it's not aligned. And then finally do a table shift to that point, go in the room, check your lasers, and see that that they are on the off-axis point. And then re-image it, and this should be in perfect alignment. So you can use one phantom like this to do a number of different tests. On the Electa program, it actually shows you what those offsets are. And then when you re-image it, you can see that it's perfect. The same object can be used for cone beam CT, CBCT, cone beam CT. So in our clinic, we use KV imaging every day on the Phantom, but once a week we run a cone beam CT to make sure that the targeting. I'm getting feedback again. Sorry. Thank you. The targeting and image guidance is working correctly. Another very important device that is used daily is the planar dosimeter. Many different types. This is one particular one. This happens to be the one that we use, made by Sun Nuclear. And you can see where it has different chambers located along the edges. Has a chamber right in the center. Has some diodes along the side to detect the field size. This object, this test device, gives the therapist an assurance, confidence that the radiation output of the machine is going to be consistent, is actually correct that day. So the therapist will set this device up and go through a protocol which the physicist has set for the therapist. And it has to do with field size. The protocol will also specify what the output of the machine should be in the center for a given number of monitor units, typically 100. But it also, very importantly, gives the therapist a number that correlates with symmetry, beam symmetry. Is the beam symmetrical, this side to this side, from here to here? So flatness and symmetry can also be monitored with this device. So this device is useful for three things: for field size, for output in the center, and for flatness and symmetry. Now, interestingly, flatness, the parameter that we call flatness, having to do with the horns of the field, the shape of the beam profile, flatness is the most sensitive parameter for determining beam energy changes. Not depthos. Depthos along the central axis is not that sensitive to changes in beam energy, but the flatness, especially at shallow depths. This device happens to have at least a centimeter of tissue equivalent material before the detector. So it is looking at beam parameters almost at D max for a 6x beam. But if the device senses a change in flatness from day to day, then that's an indication of changes in beam energy. It may mean that a thyrotron is changing. It may mean that the magnetron is changing. It may mean that the RF driver is changing. So beam flatness is the most sensitive indicator of beam energy changes. This device gives assurances that the field size is correct, the flatness and thus the energy is correct, the symmetry of the beam, is the beam properly steered, that's correct. And finally, the output, is the output correct? Here is another device, does the same thing, being set up by a therapist or a physicist. Notice the small water tank in the background here. This is a small 1D tank. Small 1D tank with a hand crank on it. Actually, it's not even a servo controlled tank. This is the old fashioned one with the hand crank on it, and it still works fine. On a daily basis, the X-ray output constancy and the electron output constancy of output, is it changing from day to day? Must be within 3%. That's the action level. There is a program software which looks at the device. So here's the QA3 device. And here it is set up in my clinic for an electron beam measurement of flatness, symmetry, and output. Now the numbers appear here, and if the numbers appear in red, that means it's failed. But if the numbers appear in green, then that means that it has passed for that day. It's a daily check, and you can see here that the physicist has established protocols for each machine. There's 3 linear accelerators in my clinic. So there's different energies for all the 3 linear accelerators, and it can be tracked on a daily, weekly, monthly, even yearly plot. So the physicist can check this every day and see that the test has been performed. Does it meet specification, and how is that trending? Here's a good example here. Nothing is red. Everything has passed. Notice how it shows numbers at each detector, and you can see the effect of flatness here. So it's very close to 100 in the center, but look at this, 2.5%, almost 3%. So this is a measurement of beam flatness. And from diagonal to diagonal, look at the flatness. There's nothing wrong with that. That's very typical for these beams to have a profile like that. And it's the comparison of these flatness figures to central axis that gives it a determination that the energy has not changed.
Frank, we
Yes.
have a really good question.
Yeah.
Is the daily QA3 also suitable for cobalt?
I'm sorry, for what?
For cobalt beams?
Oh, yeah, absolutely. You can use daily 3. You can use that for cobalt. It's going to be very consistent for cobalt, but it will check field size, and it will definitely check the output at the central axis. And since it's a cobalt source and not no flattening filter, you can be assured that the energy and the flatness and symmetry are going to be pretty much perfect day to day. But the important parameter that it would give you is output. Does the output agree with your decayed output? So you would have to be able to set that range. You would have to monitor that range consistently, and probably have to change it once a month depending upon the decay scheme. But yes, it could be used to double check that your decay calculations are correct.
And Frank,
Yeah.
so the daily QA3 is a very expensive device. So if our clinics wasn't able to afford a daily QA3, how would you recommend that we perform these tests on a day-to-day
Yeah,
basis?
very great question. I'm going to go back a ways here. Yeah, right here. So see this lower right picture right here? That's a device that I made myself. I took a plastic cube that holds family photos. I bought it for $1 at a discount store, and I accurately placed graph paper on it. And then I got a slab of plastic and I drilled it at 3 points so I could put these screws in it. And I have a very cheap device to test geometric parameters. It has graph paper on the bottom for field size and graph paper on the sides to test the lasers. So I made this myself many years ago, and we're still using it today to test geometry. Now, as far as output goes, if you don't have the funds to buy something like a daily QA3, at the very least, you should be able to use, hopefully you have a diode dosimeter in your clinic, or maybe a transit or secondary dosimeter that you can put into a phantom and just set up that cube on a daily basis, at the very least, to check output. So a diode or a dosimeter, ionization chamber, small ionization chamber, placed within a cube at a fixed distance with a fixed SSD and a fixed field size and a fixed number of monitor units, should give you the same result day to day to day. Now, if you want to get even more creative with that single device, you would put it in the center here for output, but you could lay a piece of graph paper on the table and you could check it here and here and here and here and check your symmetry and flatness, because it will give you those numbers. So you even at the very least, if you don't have the funds for something as technical as this, you can still make up a device with either a diode or a chamber and still check output, flatness, and symmetry. And you would have to set it up on a piece of on graph paper and have ranges, and the therapist could do it that way. A little more time consuming, but still gives you the same confidence that the machine is running correctly that day. Very good question.
Thank you, Frank.
Yeah. So we were here where I said good results, but also if you're using a record and verify system, Electa has a record and verify system. This is the one that I'm familiar with. It's Mosaic. Now, the Mosaic system allows you to program into an assessment sheet, LINAC, morning and weekly QA. Look at this. So the physicist has programmed into an assessment in Mosaic all of the things that the therapist checks on a daily basis. It checks the mechanical parameters of the machine. It looks at lasers. It looks at cone beam CT and KV. Are the safety checks working okay? And then weekly QA for a weekly port film. But look at this. So you can build into a Mosaic assessment. So you don't even have to record these things in a separate logbook. You can build it right into your Mosaic record and verify system, all of the tests that you want to perform, and have the therapists fill those out on a daily basis. And this makes a great logbook and a great record that you can show uh, people that are interested in assessing the quality of your department. In the US, we get inspected by the state occasionally, and we get inspected by accreditation bodies like the American College of Radiology or the American Society of Radiation Therapy, Oncology, Astro. There are several agencies that come and will audit your department for quality. And when you have this kind of record, it shows that your therapists are doing the daily checks that are necessary to ensure safety and accuracy for that daily treatment. So this is a nice way to embed it into a record and verify system if you have one that can do this. This happens to be Mosaic. I want to point out a very critical test. I know that the topic today was daily QA and IGRT. And I want to point out, however, a test on the Elekta Linac that is so critically important. And the same can be said for a Varian Linac too. There are different ways to run this test, but I'm familiar with Elekta, and this is the one that I'm going to show. And this is the Physicist running a monthly KV-MV Isocenter testing. I consider this one of the most important tests, along with output, flatness, and symmetry. Many times this is called the Winston-Lutz test. Elekta provides this with their linear accelerator. This is part of the package. When you buy an Elekta linear accelerator, you get this imaging device that the service engineer will use, but I encourage the physicist to use it also on a monthly basis. At the end of this rod is a ball bearing. You see it right there. And there's a cross here, both in the sagittal plane and in the up and down left to right. To run this test, you set the crosshairs, on that BB. And then you do a Winston-Lutz test, which means that you run the linear accelerator in the MV mode and you image that ball bearing 8 different ways. You image it at all of the major coordinates, all of the cardinal angles, and you also rotate the collimator 180 degrees. Now, there is software in the Elekta Linac to do this. It's called FlexMap. So within Elekta, there is a software package called FlexMap, and it allows you to test the accuracy of your KV imager versus the megavoltage X-ray beam. I can't stress how important this is in this time of image guidance radiotherapy. This is so critical because your therapists are going to use KV imaging to locate the target. And then they're going to do the table shifts to that point, at which time they will turn on the therapy beam and deliver the large doses of radiation. How do you know that what you've targeted is exactly where you're treating? And you don't know that unless you run a test like this, which many times is called the Winston-Lutz test. So you set up your lasers at this ball bearing, and then you image it. 2 images at each cardinal angle. So that's 8 images altogether. And then a software program within the Elekta package, within FlexMap, there's a software program that will find that BB in the center of the radiation field. So you'll see a radiation field and a dense BB in the middle of it. And the program analyzes where that BB is within each radiation field and then calculates how far off the center is from the center of the field. Usually it's within Usually it's within a millimeter. Usually it's within a millimeter. You then use these micrometers, one for each axis, x-axis, y-axis, z-axis, and you adjust the position of the BB to the exact center of the megavoltage therapy beam. So the program will tell you how to make these adjustments, X, Y, and Z. You adjust the BB because it's never right the first time. You always have to adjust it a little bit because the lasers aren't going to be perfect. The lasers might be off by a half a millimeter or a millimeter. But by using the software to analyze the position of the BB, you set the BB in the middle of the radiation field. Okay, now the next thing you do is you take a cone beam CT of that exact location and you use the image guided software to place the exact center of the image to the center of the reference image. Now, if you've done this correctly, and if your KV and MV isocenters are exactly the same, you'll see the purple superimposed on the yellow, and that means that you're delivering your beam precisely within a millimeter to where you think the radiation is going, or vice versa. The radiation beam is delivered within a millimeter to where you're imaging. In fact, this system is so sensitive on Elekta that you can adjust it to within a quarter of a millimeter. That's how accurate you can get by using these precision micrometers and this Winston-Lutz test. You can get to within a quarter millimeter accuracy of imaging isocenter and megavoltage isocenter. Don't forget, the machine has both imaging and megavoltage, and they're 90 degrees apart. So each has its own isocenter. The two have to be perfectly aligned. If you want to target an image exactly where you're treating, you need to run this test to make sure that your image isocenter precisely coincides with your MV isocenter. This is called a Winston-Lutz test, or Elekta calls it a flex map test. Another thing you do with this test, at least what I do, is once a month, I also check the accuracy of the table shifts. So I will take the BB and I will offset it, usually a centimeter in each direction. I'll offset it. Like here, I took the table and I dropped the table down by a centimeter. And then I moved the table left and right, left to the left a centimeter. And then I moved it in and out by a centimeter. And then I recone beam CT. Obviously, it's going to be off from the reference image. This is what it looks like here. It shows you that where the BB is not where the reference is. It's off because I deliberately put it off. I cone beam CT it with this offset. Then I use the software to correct it. So in Elekta, you would superimpose these images. You would move them with your mouse. The machine, the Elekta software, calculates the offset, and then you adjust the table to that point. You go in the room, you look, and your lasers should be right on the crosshairs if everything is aligned up and working correctly. So this monthly test not only tests the KV-MV isocenter, but also can test the table shifts. Now, the therapists, I know the therapists daily are checking table shifts, but does the physicist check table shifts? And I never want to be in a position where the therapist is checking things that I don't double check. So the therapists are doing a great job checking table shifts on a daily basis, but I like to come in once a month and run this ball bearing Winston-Lutz test to make sure that KV-MV isocenter are the same and that the shifts are working correctly. It's a short lecture today. That's it. But we covered some very, very important aspects of daily QA, especially in summary. Make sure that the geometric parameters of the machine are correct. Make sure that your imaging IGRT guidance is correct by using a phantom, offset phantom, and making sure that you can shift to the right place and treat there. The output of the machine, or output constancy, symmetry, flatness. And then I wanted to mention this very important monthly test that physicists should run to make sure that the MV, KV isocenter are the same and that the table shifts are correct. So I am going to end the lecture here, and I thank you. We had a lot of people participating, I see. And if anybody has any questions, please feel free to text Tia or ask them directly. But it's time for you now if you have any questions. And